all this architectural aesthetic for all this cornice work, there's a reason for it, and it's not just aesthetic. So this is a really important thing to understand. This is a building where I live. It was built a few years ago, and this is a really good example of an architect trying to build a sculpture and not a building that works. So you can see no overhang on the left-hand side here. There's really nothing. There's no overhangs and no protections for this cap here. These are soaking wet, right? This is a day after the rain. These are all soaking wet. You can see the rain pattern here, how they all get wet. Notice the corner, because there's no protection around the corner. Here's a better example on the right-hand side here, a little closer up. Same thing here. Here's another side of the building. This is older water damage. This is a brand new building. And the other issue that I have is this is a vented cladding. It's a spaced cladding. So between every one of these pieces of cladding here, there's a gap. And then behind the gap, they have their rain screen. And then behind the rain screen, whatever that space is that they have behind there, behind the rain screen, they have roll goods, a material product that's supposed to protect against that, but it's not designed to protect against driving rain and high winds. That's one of the reasons I don't like this, because you're deliberately bringing water into where you don't want it, instead of trying to keep it out and dealing with moisture that gets in instead of bulk water. And then the other thing is that these get clogged up with bugs and all kinds of dirt and everything else. So what's the point? Anyway, you can see what's going on here. Look for these details as you're running around. A couple of kinds of moisture we're talking about. This is bulk water movement, and this would be rain. On this one, hole in the roof. You can see the damage here. Capillary action is the molecules of water act as a chain link, like on the right-hand side here. So they get sticky. Water is interesting stuff. They get sticky, and then they hook onto a porous material, and then they will drive themselves up, and they'll keep crawling up. And we know this can be very high elevations, how high this water can climb. And all you have to do is take a look at a redwood to understand that. These things wouldn't be that tall if they couldn't get capillary water all the way up to the top. So capillary action and bulk water moving, those are two of them. We have drainage problems here. Here are the details. This is a detail that I like. I like a solid pipe with quarter-size holes, and I'll talk about that in a second. This is the example, the way it is prospectively drawn, schematically drawn, but they don't show, well, I guess they do show a wrap around here as well, this filter fabric around here. And all this filter fabric does is protect the fines from the backfill from getting into the pipe. But you can also see, even if they do get into the pipe, these quarter-sized holes are going to allow any of that material to pass through the pipe. So this is the kind of pipe I like. This is the kind of pipe I hate. The slots are too small. They're completely around it instead of on the bottom, because this is what we want it to do here. We just want it to fill up to here. This middle lower section here, this is not good. And that's because, not because of the fill around it, but because of the mesh around it. There isn't enough free draining material around the pipe like there is here. Here, it's just not enough. And of course, they're using the same pipe here. It's not smooth, has a lot of resistance, picks up debris, and you can't clean it out. You can't run a rooter through it. So this is the Schedule 40 drain pipe. That's the stuff I like to use. I like to use the non-glue stuff, so if you ever have to repair it or anything, you don't have to cut basic sewer pipe. Another great example of very poor planning. Why don't we just drain everything back to the house? And I mean, you can see it here, even on, so this one was not finished its earthwork, this house here. The one above it was, and they've got all their gravel, but they're still sloping back to here. So this guy is not only going to have a basement problem, he does have a basement problem. And I'll show you that a couple of slides down the road. Here are details of details that are highly problematic. Just bring your attention to a couple of things. This block, this is called rostra block. I don't even know if it's still made anymore. Highly porous, nothing more than styrene prill aggregate in a cement base, very porous, low R value, even though they said it was somewhere on the moon for R value, and it's not. That's just a sidebar there. I don't recommend it except in the desert, if it's even still around. So let's talk about this first. So how's the water going to get uphill here? We don't know how that's going to work very well. There's no protection on here. There's no waterproofing. There's no water repellent, anything, damp proofing on here. This has not been cleaned off to accept it. What happens is you get something like this on the left-hand side. Water gets in under here. It's very poorly done. You got a big open gap here. This drain mat is supposed to have a terminal strip on top of it, and it doesn't. That's another problem. It's not about the backfill or it falling down. It's about it separating from the wall over time and getting debris behind it. It's also really not connected to this pipe. This is this. It's just not connected. It really needs to be. It really needs to have this drain mat go all the way down to the filter fabric. Of course, there's no filter fabric as well, as you can see around the pipe. There's nothing. There's tons of debris in here that's bad. So if you're looking at drainage systems, pay attention to what they're supposed to do and how they put them together. This is a little bit more about insulation, and this is really in floor spaces. We're talking about areas like this that get missed easily. Even the sill gaskets, you really should have a seal right here, some kind of flexible sealant that can move. We've got actually 3, if you count the rigid, 4 different materials. Each one has a different coefficient of expansion. So we need something that's going to work with all these different materials. Gun foam doesn't work. It's not flexible. I'll say it now and we'll go through it later. So gun foam doesn't work very well. You've got to use a sealant that's going to be able to work with all the different material, all the movement of different materials. Cap the top, cap the bottom, and then you're going to have insulation on the floor here, bottom left, same kind of thing. I'm not a big fan of the 2-foot rule for the board underneath and then leave the whole center open. I've seen too many images in the wintertime where the snow and the ice stays on top of the areas where the rigid is, and in the center it's all melted away, soil underneath melts it all away. Again, another sealant on the top of everything. We're trying to control moisture here and air. That's the most critical thing. This is a foam system in here. You're certainly welcome to use that as long as it's installed correctly. That's the problem. So we talked about this foundation stuff. So here's a basement. This is up in Canada. I was up there a little over a year ago. And what they did was they did the classic thing. They love to do this in Canada. They love to use plastic on the walls. And it's really because there's very little understanding that you could have an air barrier that's permeable. So plastic is considered an impermeable air barrier. It's definitely a class 1. That's between 0 and 1 perms. But you can see the results that happened here. These were sticking to this concrete because the moisture got frozen. You can see it here on the bottom. Here's the grade line. I didn't even have to go outside and measure because you can see it. You can see where grade is here. As it melts, water drips down. You create problems on the bottom of the sill and through here. You can see the draping on the upper right-hand side here. This was really, really wet stuff. So unfortunately, including the inspectors and the building officials, because the rule says that you got to have an air barrier, it doesn't say that it has to be impermeable. So every time I see a basement with a water problem, it's always because it, unless it's running in under the foundation, but on a wall system, it's always because it's using an impermeable air barrier. These should only be used in very hot, humid climates or extremely cold climates. The other problem is they get installed incorrectly. So now you have an impermeable layer that you put staples in to hold it together. So every staple has 2 holes. Every time you have a stud, you're going to have 20 or 30 staples in it across this entire building. And then you're going to cover it with drywall and put another 30 or 40 holes per sheet in it. So what happens is there's enough moisture from the interior that gets driven in the wintertime because everything goes from more to less, and it's warm inside and cold outside. It's going to drive the moisture through the drywall, which is highly permeable and very absorbent. And what's going to happen is there's going to be enough pressure to get it through those holes, but not enough pressure to bring it back out to dry to the inside. And that's the reason all these things fail. Use a permeable air barrier on conditions like this. Worst thing you can do is have a hole. This is like a 1-inch hole. So for drywall with a 1.5-inch hole at 70 degrees and 40% RH, you're going to get 30 quarts of water. It's 100 times more than just diffusion, okay? So this is a problem when holes are not sealed up. You can keep adding up small holes over time in a building, and if you actually measured them, you'd have a very large hole in the house. So you don't want to do that, but the point of this is that most of the water is going to be transported by air. This is air hole, big air hole right here. Diffusion is going to be a lot less. So that's what we want to do for vapor retarders. We want to slow down moisture movement from one side of the assembly to the other. Doesn't matter which side. We like to have it working for both the interior and the exterior. One will do if it's done correctly. We just talk about these a little bit. Vapor perm. There's a difference between a retarder and a barrier. Okay, so don't get the words confused because everybody confuses them most of the time. If I said most, everybody confuses them all the time. That may be a better way to say it. So the retarder is just going to slow down any diffusion that gets past it. There are a lot of different kinds of really good vapor retarders, and craft-faced bats, that is the original smart vapor retarder. It's, it's a cellulosic material. It's paper, and paper is absorbent. And I can't remember if I got a slide in here of what that looks like. We'll see as we go. But basically, it's a wide open pore, and water gets into that, the paper, and it starts to swell because it absorbs the water. And as it swells, the holes get smaller, the pores get smaller and smaller and smaller. And yes, they don't let any water out, but they don't let any more in. And then the next step is as it dries, these pores open up and the water gets transported out, back out. And that's what we're looking for. So it's actually a variable vapor retarder, kind of like all these new smart vapor retarders, smart air barriers. So they slow down and control. It's a valve or a throttle. Function of a barrier is completely different. It will prevent the migration of water vapor. So, and where you place them, what kind you have, and what the permeability rate is very dependent on your climate zone and the use of the interior space. Is it a warehouse? Is it a home? Is it a hospital? All these have different requirements for the amount of moisture that they need to deal with. So that's something to keep in mind. So different materials transport more water differently. Now this is plywood. I'm a big plywood fan. OSB is fine, but I'm a plywood fan. I'm an old crotchety guy, and I've used this stuff for years and years and years, and it's never treated me poorly. So I've also used OSB. I like plywood. So the thing that's interesting about plywood is we all know that plywood is made by layering sheets of very thin material, and they all get adhered together in a press with a phenolic style resin. What that does, it allows the material to absorb water more readily because there's nothing on the surface other than the actual sheeting material itself. Actually, the peeled lumber is the only thing that's on the face. And then we have layers all across, these linear layers. So the water is able to get in and redistribute itself laterally, and then it has not quite equal, but pretty close. It has the opportunity of releasing moisture in both directions, interior and out and exterior. So this would be the exterior, let's say in a rain condition, and this would be your interior. We want drying in both spaces. OSB is a different animal completely. Basically, it's near wood. It's not real wood. They chip up a bunch of wood. They put it in a big boiling pot, and they open up the pores by doing that. Really get it soft and mushy, and then they spread them all out, and then they put tons of glue and resins on them, and then they press them together, and then they coat them again with a light resin, and then there you go. So they're way more dense than plywood, and they have a very different way of redistributing water. You can see that most of the water gets reflected back where it's going, and any of the water that gets in does not allow it to dry to the interior. So as long as you have a rain screen on this and this is installed properly, you're going to do fine. But most people do not use rain screens. So I mean, that's an issue. It's really important. It's not a code requirement, but it really is best practice, and it's actually what you want to do all the time. And I don't care what climate zone you're in, it's an important feature to add to your assemblies. Air barriers, a little different ball game. So air barriers are to control not air, because if we can control air, we can control a couple of things. We can control pressure to a little bit, not very much, but mostly what we can control is moisture, because whatever moisture is in the air, we don't want to get back into our assemblies. And that can be walls, floors, roofs, ceilings, what have you. So these air barriers, they're really designed for one primary purpose, and that is to control airflow. And it should be understood that you need to do that in both directions. I know that the code talks about an air barrier on the exterior, but they imply many times throughout the code, and I don't have the rhyme and verse in front of me, but there is an implication many times, and I'll show you examples of that down the road through the slides, highly implied that you need two air barriers. You need one on the inside and the exterior. Best building science practice is, yes, you need two air barriers. And that's because there's moisture on both sides of the assembly. Climate changes, we have, at least we have two seasons here, rain and no rain. I live in northern Washington State. But we usually have 4 seasons in many of the climates. And because everything goes from more to less, high pressure always goes to low pressure. Water, wet goes to dry, and warm goes to cold. So as the seasons change and as the interior environment changes from heating to cooling, then what's going to happen is moisture is going to move in moisture and energy are going to move in 2 different directions depending on the time of the year. So we can talk about this a little bit more down the road, but I just want to make sure that you understand that we're talking about airflow, and we're talking about 2 air barriers, one on either side of the wall assembly. So that's that one. These are some details that I really want you to take a look at and see what's going on. So there really isn't an inspection that I know of a weather-resistant barrier, and that's a problem. So this is a problem. right here. They're already siding the other side of the building when I took this. This is a problem here because the tape is installed incorrectly, specifically on this side. This one goes over this one, and this one should be shingling over that one. So who knows why they do the things that they do. Gaps right next to the concrete. Nice little gap here, nice little gap here. This should have been folded over and the tape on top of it so that things are shingled. If water gets behind the tape, it fails, it flows back, shingled all the way down. So this is the one I like the most. I see this quite often. This is what I call tucking your raincoat into your pants. And this will do no good because it will go right into the plate. I guarantee you there's no sill seal on the inside, no sealant on top of the gap where the sill seal is, not only in the inside, but I can guarantee it's not on the outside. And this water is just going to run down any little capillary crevice that they can find along this, and it's going to get right into the building. And 10 years down the road, they're going to be replacing wall systems. So you need to pay attention to that. These are the results. This is what happens when you have these failures. Now, this one here, I can't say 100% for sure, because if there was a vapor retarder on here or Tyvek or some other weather-resistant barrier, you would probably see some of the remnants of that behind the siding here, and I don't think there was any. This is plastic here to cover, to bring all the debris out so it doesn't get all over the gravel. But you can see what happens when water gets in and there's no way for it to get out because the siding is right up against here. No rain screen, no WRB, nothing. This is an interesting one because there were certain areas in here. I don't know what was on the cladding of this system, but obviously certain areas. To me, it looks like what happened is this gap between the OSB all the way across here, you know, where they've got sheets stacked, and you can see the same thing here. It's all happening there, right at that line. So my guess is that warm air got through there, hit up with the cold, condensed on the outside, and there's the problem. This is a Habitat for Humanity house on the bottom. Problem is, if you haven't already spotted it, the WRB is in the wrong space. So this is a semi-impermeable material. Some people call it impermeable, but it really doesn't let enough moisture out when conditions are right. This should be a wrinkle wrap, a drain wrap, or something with a texture to it to create a capillary break, and that goes on the sheathing, taped, sealed, nail spotted, everything, cap fasteners, do it right. And then this goes on top, the blue board goes on top of that, and this little capillary break behind it allows moisture that comes from the inside of the house to drain down or convect up and get rid of it, because the Tyvek is like, what, 23, 30 perms, somewhere in that neighborhood, depending on which one you buy. And this is like class 1. It's, you know, less than 0.1. It's very impermeable. So as we move out an assembly, we want the permeability of each layer as you're moving out to be a little bit more open than the layer behind it. Okay, so you do have ways to get rid of that moisture. In other words, think of a funnel pointing out with the opening of the funnel, not the tailpiece that goes in the bottle, pointing out. That's kind of the graphic that you want to look like, where the outermost part is the most permeable and then the least permeable on the inside, or the sheathing, let's say OSB, as an example. More examples. This is not taped. They did use cap fasteners here. I'm impressed. They put them on the correct schedule. I'm impressed. I'm not impressed with this. And this is the reason why. There isn't even enough flap over here to cover the whole thing. This is really not tight to the top. This should have gone in and over. This piece should have gone in, over, and down like this. This should have come all the way up. They don't have that piece here. And then this part of the Tyvek goes over the top. Everything is shingled. The rule is down and out. That is the rule, just like mountain climbing. If you're doing rock climbing, your carabiner wants to face down and out. That's the gate. That way you don't get into trouble. Same thing here. Down and out is the rule. This was a test done by Building Science. Stebreck and his crew put this in a chamber. The entire wall assembly was treated identical, except this is OSB and this is plywood. They had one test area that they were actually looking at, but you can see none of that makes a difference because this entire sheet of OSB is completely destroyed with mold. This is a problem. And the problem is there was no drying potential enough to eliminate this. So a lot of times I'll say that really we don't care too much about how wet things get, but we really do care a lot about how quickly we can get them to dry. That's really, really important. So I'm going to take this, laser off here for a second. Bear with me. I got to find my cursor. I don't even know where it is now. Oh, there. Let's see. Bear with me. Sorry.
No worries. Yeah, and that's something I can tell you just from doing the field training. Can you hear me, Rick?
Again? Yeah,
just
I
from
can hear
doing
you.
the field training I've been doing, the #1 problem I see in residential construction in Texas is in relation to the weather resistive barrier. There isn't a specific inspection mandated by code for a weather resistive barrier. Kind of blows my mind because that's just going to be one of your main failure points. And just the head flashing above windows, not doing the Tyvek right above windows. 99 times out of 100, the Tyvek's not done right above the windows. And so I'm glad you mentioned that. And just for all the inspectors on the phone or on the webinar, next time you go out to a house, just really pay special attention to that weather resistant barrier and how they're doing it. Go look at the method. There's a few different methods for a Tyvek install over a flanged window. Look through those installation instructions and you'll be surprised at how few times it's being done correctly in the field. That's all I had. Thanks, Rick.
Oh yeah, thanks, Jason. Good point. And one of the things about head flashings on windows is I rarely see the ends of the flashing. Sometimes they're extended, sometimes they're cut right close. The two problems with flashing is a lot of them are tipped back towards the house. That's not a good idea. Instead of sloped away to the outside, and that the ends are not turned down. So even if it's sloped correctly, you've got a wider gap against the wall instead of where that horizontal piece of the flashing, that pitched part of the flashing, covers the window trim. On the back side of that, there's an open hole. So it either has to be filled with a sealant or it has to be turned down on the edges. Most people don't do that. And again, when you get wind-driven rain, you're going to be in trouble because it's going to get right behind everything you don't want it to get behind. So that's what's going on. Now this is, well, obviously this one's behind a toilet, and this one was a kitchen cabinet up against the wall. So, understand the grass board is not so dense fiberboard, or it's like a fiberboard, highly porous, made out of, wood, very absorbent. GREENBOARD, if you do not understand the difference between GREENBOARD and standard drywall, the only differences are that the face is green so you can recognize it. It's still paper. It's no different than this paper here. It may have a small bit of water resistance that may be immeasurable, but the thing about GREENBOARD is it's made mostly of clay. There's more clay than gypsum in it. So what happens is when it gets wet, it doesn't fall apart. That's what GREENBOARD's all about. It has nothing to do with moisture transfer, staining, mold, or anything else, and you can see that here. So I wouldn't waste my money on this stuff myself, even in a wet area, because it's the wrong material, as far as I'm concerned. Foam. This is very interesting. Now, this is a closed cell foam. Remember I said earlier that foams are not flexible. Open cell is more flexible than closed cell, but closed cell is not considered a flexible material. So this is after a while in a house where things are being dried out and you can see the separation lines where the arrows are pointing here between the foam. So you do this on one cavity, and if it's on both sides, I can't tell because I can't see the other side of the stud. But if you do this in one cavity, you're gonna have easily an 1.5 inch hole, easy in there. So now you got moisture problems, but you just lowered the R value maybe by half of that particular cavity. So gaps are no good. It's not considered grade 1 installation, less than 2% voids, compressions. And I don't even consider that grade 1 myself. I'm way more particular than that. But anyway, you can see the problems where inflexibility is creating a negative result. Here are areas on the right-hand side where the foam actually didn't fill up everywhere. You can see it, and all these little holes add up, and you're paying so much money and taking so much time. You got to stay off the job, even though they don't. Stay the 24, 48, or 72, depending on the program you're working with, off the property. To be able to come back and correct this, because the next thing they're going to do is start covering walls. But again, you're losing precious thermal value when you do this. Lots of different examples of open cell. So the problem on the upper left here is that you're going to have these cavities when it's not filled flush once it's scraped down. And then you're going to get convective air currents in here that can create all different kind of challenges with heat loss and, you know, moisture accumulation, etc. It's more porous and more flexible than closed cell foam. It does have that advantage. The only problem with it is you're paying a lot of money just to get air sealing, because the R value of this stuff is around 3.3 to 3.4 per inch. You can get a fiberglass bat at 4.4 per inch, just as an example, and air seal as you would for a lot less money. Same problem. These do not expand as we think they will expand. This is poor. This sagging is usually poor mix. I can tell just because of what the foam looks like. It's a poor mix in here, and there are a lot of reasons for that. This is the thermometric report. It was done 2015. This is a 3-part report. This is the 3rd part. They had foam manufacturers selected and come in to do this under lab conditions to get it right. And even when you have the highly selected professionals to get it right, looks like they can't. This is a huge problem with foam, too many variables. And I can speak all day on foam. We don't have time for that today, and you probably don't want to hear me do that. But again, here you go. This is convect right here. It's not convect, excuse me, it's concave. So again, you're going to get air currents through here. Even though he may have filled it, you can see in the center here that it's not as filled as it is on the right-hand side. Things you can't see in the middle of the foam: substrates, internal voids. There's another substrate on the left here. I'm going to click through these things. There's another one, separation from the substrate. Again, here's the closed cell foam, just so you can see the difference. But here, this is what happens when you have poor mixes. That's not correct. And these are left this way. This is the way I found these ready for cover. This is, again, internal void, more separation. And this is what happens when lumber moves with closed cell. Again, this is the gap that's left. This is the foam from here to here. This is all foam. And then, of course, this is lumber. And you can see what happens when they shrink and twist. You open these gaps up, and you're in a big world of hurt as far as thermal energy goes. Same thing here. You can't tell if the cavities are filled. And you know, when you want to fix it because you're not going to come back, well, just put your favorite snooze can in there and that'll cover it. Make sure that the air gap is covered, not to mention all the stuff here from the poor framing. These are critical details, not to mention that the person who's the owner or the developer is not getting what they paid for. Try and get a foam guy back to correct. Pretty hard to do. Here's an example of, again, this is about air getting into an assembly. So this is a roof system. This is in Southern Oregon. And of course, they side stapled. And even though that's legal by code, it is not best practice and it creates problems. And the proof is in the pudding here. So what happened is they did a couple of things. They improperly stapled. Even the side stapling is not properly stapled. They used really small pieces to fill in things instead of using fill bats. So they got gaps more than they may have in the first place if they used, longer bat material and saved their scraps for other things rather than filling in a full cavity with them. The other problem is that they really didn't have enough air. This is a vented assembly. They didn't have enough air moving through the roof in order to prevent condensing. Their baffles were crimped right in here, and then we took the roof off to see what was going on because when they called me in, the system looked like this on the upper left-hand corner. By the time I got down there, this is what it looked like, so we couldn't even do it from the inside repairs. So they had to take the roof off to do it because they had so much mold that it was the only way they could correct it. And they refused to take this down, which would have been much easier. Take them down a piece at a time, label them. It's all tongue and groove. All the nails are buried. You can use a pin punch and get right into there and put them. Anyway, they could have done that, but they didn't. They ruined an entire roof covering and all the OSB on top of the roof for no reason. Anyway, so this is the other problems. They've got these to hold on to the lookouts, these blockings in here. There just isn't enough airspace here. They're right up to the top of the rafter, as you can see right here. Changing the subject a little bit. Oh, wait a second. I gotta go back. I don't know why this didn't show up. That's what I'm looking for. So this is how we fix this baby. So this is 1.5 closed cell polyiso, rigid foil facing down to prevent interior moisture from getting into the assembly. Remember, it's a vented assembly. So if we prevent moisture from getting into the assembly and have a way to vent it out through the ridge vent and the eave vents, we're fine, okay? But you gotta have that airspace. I can tell you that even though the code says 1 inch, some of them may say 1.5 inches, it's not enough. You gotta have 2 inches for it to work. Whether that's practical or not, that's another story. But you gotta have 2 inches for it to work properly, unless you're really good at 1.5 inches. So what we did was polyiso because we couldn't get at it from the bottom. I would have preferred to tape it from the bottom where the pressure pushes the tape into itself rather than the pressure trying to lift it, from the underside. But this is all we had. There's sealant under it as well. So polyiso goes in. Right below this is nothing more than that tongue and groove sealing that I showed you. And then on top of that goes the insulation. They're still going to have some problem here. They do have air movement because of these troughs throughout. And they're going to run these all the way up to the ridge. So that's the way they fixed it. Haven't heard a word. It was a couple of years ago. So we know that it works. Unvented roof assemblies. So you go from a vented, what we just looked like, to a vented roof assembly. I'm going to back up 1 second. I just want to make sure I'm on the right screen. Okay. So this is an unvented assembly. And really, the thing about unvented assemblies is you have to make them as airtight as you possibly can. If you don't do that, then there's something in between a vented and an unvented, and you're going to run into problems. You can't have an innie and an outie. You can't have 1 foot in your truck and 1 foot on the pavement. You've got to be all in when you do this. And the key to this, when using any kind of fibrous insulation in the cavity, any kind, That could be rock, it could be glass, it could be cellulose, it could be wool, it could be denim, anything that's fibrous in this cavity right here has to be protected from condensing by putting enough insulation on the top. And again, it does not have to be impermeable or vapor semi-impermeable like the blue board shown here. It can be anything as long as you keep the sheathing warm enough, 45 to 47 degrees. 45 is absolute minimum. I like 47 degrees. You can keep this at 47 degrees, which is what this insulation is doing. It's preventing, it's condensation control. That's all it is. Yeah, you're getting R value out of it. The main reason is condensation control, and it's dealt with by climate zone. So where we are, R10. But if you're in Alaska, you need R30. That's just on the top of the roof. That's not what you need in the roof system. You might need an R60. So you can do 30 and 30, or whatever, however you decide to do it to split it. Key is the colder it gets, the more condensation control you need to keep that interior first condensing surface as warm as you can. This is from Hammer in Hand. Here's a great detail of what we were talking about. Notice that the parapet has insulation in it. It's almost always forgotten. Worst case scenario is if they run the wall all the way up and then hang their joists. Bad news, because now you have all this connection all the way into the wall, no matter how well you seal it. So that's one look at it. Sloped roof, same condition. This happens to be one I did for California guy, and this is just metal roofing here. The tabs, I've labeled everything, but you can see we've got condensation control based on what they need in climate zones 3 to 15 in California. They've got 16 zones or 15 zones. We've got 8. So it's California. Just deal with it. R5 is what they need in California for 3 to 15. Get their R5 up here. They can fill this with insulation. And again, all the layering is critical. The permeable peel and stick, impermeable air barrier here for unvented. There are a lot of tricks and details that have to be considered when you're doing an unvented assembly. Unvented assemblies, I never recommend an unvented assembly in anything greater than climate zone 5. It's high risk. Again, you can do this on the inside with an impermeable layer, like either closed cell foam or rigid board, anything that's semi-impermeable or impermeable, or on the outside, but the outside, again, does not have to be an impermeable layer. It can be anything. It can be rock, it can be glass board, whatever it is, as long as you got the right R value to keep this sheeting as warm as you can. This is back in 2013. I ran through a guy's house who was having mold problems, and there are a lot of issues with it. I'll just point some of them out, some of the reasons why. So these are all hip roofs throughout the entire house. There are many of them, and obviously valleys. And what happens on the connection bracket right up in here is that bottom left, you can see these areas right here. You can see right into the insulation and the plywood right here. So the drywaller can't get tight enough in here to seal these up. And nobody knew to go back and throw some sealant or something in there that they could get these in these tight spaces. So all the air is moving up into this assembly. Now remember, it's a cathedral assembly. So this is the bottom of the rafter right here, this plane right here. These are all planes at the bottom of the rafter. Other problem is these vents don't work. You have to put 4 times as many of these vents right here, these little small button vents, in as he has here. And I'll describe to you why in a second. This is a 2-inch vent on the left-hand side. I know who the manufacturer is. It's Maurice Franklin, okay? So I can go online and find this particular item, and then I can find what the net free area is. And that is the area that's left after you take away all the after you take all these louvers and push them to one side, and you take all of this screen behind it and push the horizontals and the verticals to one side, whatever is left is the net free area. So this 2-inch vent does not give me 2 inches of air. It only gives me 0.8 inches. So let's say you needed 6 inches in each cavity. You can't put 3 of these in because 3 of them is only going to get you 2.5, right? Net free area, 2.5 inches, and you need 6. So that's why I said, just the short answer is don't use them. If you see them, you're going to have to do a calculation because I can guarantee you that there won't be enough for venting. Other venting problems. This is in a, oh, it's the same place. So one of the problems that we have with ridge vents is a lot of them today still have this filter fabric on them. The problem with the filter fabric is when convection gets going the way it's supposed to and up through the underside of the sheathing, it carries dust particles and everything else. You can see in the upper right here, you can see how clogged this gets. So either use ridge vents that do not have this, or if this is on the ridge vent, I would take this off. You're probably going to ruin your warranty by doing that. My suggestion is buy a ridge vent that doesn't have leaves and meshes that they can use, and more open than this. Here is, yeah, you can't see it in these photos, but there really isn't. You should have 2 inches from the ridge down on both sides, and this one, both of these are about 1 inch. So it's 2 inches, but it should be 4 because it's 2 down from each side. Here's what happened in that house, and you can even see it's already. This was a brand new house. This was done. I was in there about 14 months after the house was built. So this is not uncommon. It's unfortunate. Other problems, products that react negatively with other products. So this underneath this window here is actually from the peel and stick that's around the windows. So what they did was they used a urethane, a 1-part urethane sealant. You can see the gray bottom right here as my pointer is showing up. And the plasticizers and the urethanes don't like petroleum-based products. So what happens is this is a drip. This is not something that was applied by caulking. It works, the plasticizers in it work on the petroleum sticky back of the peel and stick around your windows, and it releases it and it melts it, and this is the result that you're looking at here. Unfortunately, I experienced that on a deck that we built for a new roof. We followed every manufacturer's recommendation. Nobody said anything about reactions with other products. Not one of them. Not the caulking, not the Jiffy Wrap. Nobody said anything about it. And I had a hard time getting these guys to take care of this for me. So these can be very, very expensive problems. So you need to really read what the manufacturers say for their materials. This is airtight drywall. I don't know if you know about it or have seen it, but this is a really good way to get a really good interior air barrier where you're putting sealants on the appropriate places all over. And if you can do that, you've got a real good air barrier start. And then on top of the sealant goes your finished wall panel. And then you got a really nice air barrier. These are the points we have to concern yourself with. There are a lot of them. Again, I'm not a foam guy because it's inflexible. We'll see more photos of that in a minute. Advanced framing. I'm a big fan of advanced framing. This is conventional, and you can see the difference on how much lumber you save. 30% fewer spaces, 60% more room in a cavity for utilities and everything else, less bends. For plumbers, which means less fittings. Less fittings. Fittings are the most expensive part of the plumbing system. And as far as materials go, roughened materials, and if you can eliminate those and go straight up, and if you stack everything from the bottom floor all the way up to the roof line, everything is a straight line. You drill down at the bottom in the basement or the crawl space, you know that that's going to carry all the way through the roof. You got one straight run. More room to work in, less lumber, and your framing factor gets reduced by 10%. That's huge. Not to mention the amount of savings by doing anywhere between 5 and 10% less lumber right out of the gate. You don't even have to be a rocket scientist to do this. Plenty of details out there that are really critical. Very, very important details. Headers, This is one of my favorites here. We'll talk about that in detail. Raised heel trusses. This is the stacked framing I was talking about here, where all the loads are straight down. This is old style balloon framing. You can still do it with Western platform framing like they show here. Intersecting walls, one of my faves. We'll get through this in a second. Here's direction and path of the loads we just talked about. Example of a raised heel truss. You still have vent area up there, and you have plenty of space for your insulation to fill whatever the requirement is. An example, no load bearing, you don't need a header, taking up space and costing you money to install and purchase. You don't need double top plates. You don't need king or trimmers, because you're going to either put clips in here. It's non-low bearing. You probably don't even need clips. You can just use nails through it. These are really good examples. We talked about air barriers, interior air barriers. So you're, required by code, we have to have air barriers around certain things. Interior soffits is one of these things. So if you have an air barrier around here, these are the implications I was talking about. That means, here's your air barrier. So you don't build this before you put drywall or whatever installed, and then you build on top of it. Now you've got an air barrier here. Instead of having air get into here, and if there's a can light in here, forget it. It's all over, because all that heat's going to go right through the can light. We'll talk about that in a little bit too. So the best way to do it is to have a little bit of your drywall hang down before you put your soffit up. And that way the drywaller comes in with his wall, with his panel, he can go right up to the top. It's got a tapered edge. He seals it right off, muds it, he's done. This one's not as good because the blue board is held back, which means there's no way for him to hit that seam. He can only hit it on the outboard side of his drywall. He can't clear it in here. Same thing here. It's too far back. They can't cover their seam. They had the right idea, but again, the detail of the details. You got to think ahead, otherwise it won't work. Tubs, same thing. This is the exterior wall. It doesn't stop at the corners here. So this has to have an air barrier behind it before the unit goes in for a fireplace or before the tub goes in. Bad examples. How are they going to do it on this one? They're not. How are they going to do it on this one? They're not. It's already in. They got to take everything apart to do it. Not smart. Knee walls. So the thing about knee walls is that there are a lot of details in a knee wall to get them right. And one of them that's mostly overlooked, where this is actually an unconditioned space, where in here it's actually conditioned space. But because of this unconditioned space, you don't want airflow to get across. So again, 2 air barriers. Think about it, 2. They keep suggesting these 2 air barriers all the time, but they don't. There's no statement in the code that says you have to have them. Okay, here's the backing on one here. What is this lacking? What it's lacking is this block right up here, allowing the venting to go through here, but not allowing the air to wind wash the fibrous material. And the same thing here, you need a block directly underneath this, because you don't want wind washing coming from here back to here or into here. So you need blocking here. You can't see it here because you can't see the joist, but underneath this plate, you're going to need this block as well. 99% of the time overlooked. Here's the problem when you don't do stuff like that. Look at all this is brand new. This was months after the house was built. It's about 2 blocks away from where I live. Missing insulation on this one. Insulation not installed properly. Big gap right here. This is the knee wall line. Go to the other side of the building. It looks identical to that. Just a little clearer detail of what has to happen on a knee wall. Again, same thing. Skylights, no different. You need 2 air barriers. This is in an attic. This is in an attic. This is unconditioned space. This is your interior drywall. That's 1 air barrier right there. And here's your exterior air barrier. Problem is this cavity insulation, if it's a 2x6 requirement, because you got to have a certain amount of insulation, looks like it's only built with a 2x4. The way you solve that is you can put rigid foam or any other additional insulation on top before you cover it with your air barrier. Stairways, the same thing. If you don't carry your air barrier all the way through, you're going to have a break somewhere. Normally it's a 2x up against the wall framing. So this is, usually a 2x10, 2x12 times the run. So you got a huge air gap here that's going to allow moisture pollutants and unwanted air in and air out. Examples, nothing here, same thing. Anything that touches the outside wall, you've got to have an air barrier behind it. Between the garage and the living space, this block has to be here. It has to be sealed. Here's the room over the garage, the bonus room, or the frog, front room over the garage, or the bogus room, which is the term that I like because it's never too hot. It's never cold enough and it's hot enough. So
Inspectors, sorry to interrupt you, Rick. I want to call this one out because I see this missed in the field all the time. That wall separating the garage from the house, inspectors, just a fibrous material here does not meet code. You have to have a rigid material that is sealed. Sorry to interrupt. Keep going.
No, that's great. That's terrific. It's a really good point. It's very important. And the problem with it is a lot of times when they're using a truss or a TJI, then you got to cut around everything instead of all. There's so many ways to do it without having to mess it up, and it's quick and easy. God, you could hang the joists even though they're sitting on something. Put a full rim board across there and forget about it. You're done. You're completely done. So easy ways to do stuff. Cost you a couple of extra bucks. If you're doing advanced framing, no big deal. You just save 10% of your lumber right out of the gate. Not only that, it's probably faster and quicker in labor than it is to start cutting around every cabin. Other thing I want to point out here that's very important. Let's say this is just a regular typical floor section here. There's a crawl space or an unconditioned basement below it. Here's your floor system. And let's call this the rim joist right here. So if you install this graphic of the insulation, everybody has seen this. I hope everybody has seen this and understands it. And remember, fibrous insulation is built up in layers to get the thickness that they need, so that air can wash across this in this direction, but not so much in this direction. It's slowed down. This is where the R value is calculated, perpendicular to the layers of the bat. So notice it's been turned here so that the edge of the bat is not open to this to allow air movement across it. You've got to flip it around so that it works the way it was designed. That's in any rim joist situation or anywhere that condition occurs. Highly missed. Rim board headers, great. Advanced framing, even on a load, you can actually do rim board headers and you can get so much more insulation in here just by doing that. So again, it's a value proposition. You got to weigh out the benefits versus the cost. Great example of 24 inches on center. Here's the rim board. This is a gable wall, so he doesn't need anything up here. This is a load-bearing wall with this particular rim board in there. Look how much insulation you can get right in here, instead of putting a 4x header in that system. Couple of ways that partition walls intersect with exterior walls. Again, we're trying to create an interior air barrier. So if you have a condition like this, where you have a single 2x6 and a 2x4, or you have it C-shaped, and if you look down here, you see what I'm talking about, you can get most of your insulation around that. It's okay to do that, but you don't have a continuous air barrier across it. So you have to do all these sealing things around it to create it so that no air can pass in either direction across this, out of here, everywhere else, so that this becomes a fake air barrier, fake continuous air barrier. But here's the best way to do it. You do it just like we've done all of these years for decades in multifamily. Hold your partition wall away 1 inch from your exterior wall right here. Just hold it away. And then clip it with a clip on the top and you obviously nail to your joists on the bottom. You can do some ladder framing between joists on the top to do this. This wall will not go anywhere. But what it allows you to do is slip the drywall right behind it. So if you got a 12-foot partition wall, you make it 11 foot 11. Okay, it still winds up in the same place. You got an inch gap here, drywall slides through, no connecting joints in here. The only sealant you need is the top and bottom. So this is the best way to do it. This is just one example of a clip I took out of the catalog, but you can use anything that's kosher to use. Fireplaces. Now remember what's critical in the fireplaces. I don't know why my arrows aren't showing up. Oh, here they go. You need a 2-inch gap between combustibles. Lumber is a combustible. So that means this can be filled with a non-combustible material. This happens to be fiberglass. You can use rock wool. You can use, this looks like rock, this is glass. You can use anything that's incombustible to fill that gap. And what we want to do is to prevent air from going from all these different floors, the crawl space pad, and all the way up to the masonry chimney, or any other chimney for that matter, has this gap, this required gap. So you can fill it with a non-combustible. You can treat it again with another non-combustible. This will be sealing up most of your air, and then you go over with the fire-rated sealant on both edges, and now you got a really nicely sealed chimney. When you're installing caulk and sealants, it's got to have this shape to work. If it does not have this hourglass shape, it will not work. Okay, you can find this anywhere you want on the internet. Okay, it's not made up stuff. And depending on the depth and the width, depends on what you're going to have to do here for different widths and different depths. This is what happens, you know, if you're too shallow, there's not enough material here, it'll split and crack. If it's too deep, it's going to sag in here, and it's going to create an airspace in here that you don't want. This is what we're looking like. It's impossible to do this in situations like this because you can't get the hourglass shape. It's just not humanly possible. If you're going to do it in these conditions, you need a bond breaker behind the caulking. So you'd have to put a bond breaker in here, it's tape, and you'd have to get that installed nicely, and then you can seal over the top. What the bond breaker allows, it allows the sealant to move with the different coefficients of expansion. Foam in a can, inflexible, and you can't always see what you're doing. So here's a great example. Squirted it from the front side, have no clue that it didn't do any good. Missed this. These have openings all the way around them. These punch outs, these all leak. They have to be sealed as well. So you see foam like this, not good. Also, what's the first thing the electrician does when he trims out? He unrolls his extended wire out there and he pulls it as hard as he can, make sure it's tight. A lot of times you'll find this has fallen off because, again, it's rigid, it's not flexible. Can lights, I love it. So if this is an airtight recessed can and they sealed all around it, what about this? This is the junction box. Look at all the holes in the junction box, okay? It's connected by a cable that goes right into here. So where is all the air coming and going from? If you don't address this, this airtight can, by the way, which is not airtight legally by code, it's allowed to have 2 cubic feet per minute leakage rate at 75 pascals of pressure, and that's the rule. And that's ASTM 283, I believe, E283 is what that test is, and it allows 2 cubic feet a minute of air leakage on an airtight can. So airtight cans are not airtight. Put 100 of them in a house, and I've seen many more than that. Put 100 of them in a house, and you got 200 cubic feet a minute every time there's a puff of wind going out. It's 2/3 of a dryer vent. So it's a lot of air moving. More examples. This is an entire attic. I didn't have the patience to go through the whole attic, but it doesn't work when you can't see what you're doing and it doesn't expand the way you want it to. Even in here, going back, you can see another one starting right here. So you got to be really careful with foam, and just because it's orange doesn't mean it's fire rated. And you always have to look at what the manufacturer of the material you're sealing to make sure that it's compatible anyway. CPVC might be one example where a lot of these are incompatible. But again, they're not flexible, so it's risky. This is just all the nasty chemicals it contains. So I'm not going to go into that. These are some great details here. So this is in a temperate environment, so they heat in the winter and they cool in the summer. So it doesn't even matter whether this pipe is a cold pipe or a hot pipe, it's uninsulated. So when it's heating, if it's a cold water pipe, this is going to sweat. If it's cooling and this is a hot water pipe, it's going to sweat. There's no insulation on it. Geniuses, absolute geniuses. They're not thinking. Another genius move. Why don't we take all the water from the gutters and the downspouts and make sure there are enough holes in the pipe so that we can soak against the foundation before it gets into the drainage tile down below at the footing. This is separation walls right here. This is an older building. Separation walls have to be sealed for air and fire. They have to be. It's a requirement. These are not sealed. So when Mrs. Jones is playing the drums over here and Mr. Smith is listening to it, he's not a happy camper because it's just, the sound's just traveling right through the air spaces. What about a fire? Not good. What about cooking? Someone's cooking with a wok on this side with a lot of steam and a lot of oil coming out of it. I mean, do they smell it on this side? I bet they do. So again, just different examples of critical details. I know we can't do this anymore, but here's an example. You know, this is a cold air return. Holy smokes. Let's put it in the garage where we store chemicals, bring the cars in until they shut them off, close the door, the car's wet. Let's introduce some more water into the assembly. This is ridiculous. We can't do that anymore. So that's a good thing. When you're doing rain screens, I know I'm moving pretty fast here, but I'm trying to get out of here in a reasonable amount of time and not have you guys spend most of your day with me. Again, all the system is exactly the same as you would normally do. You put your weather-resistant barrier up. On top of that, you would put your furring, so you have a space behind it. This dash line here would be the weather-resistant barrier. But you need this gap, and you need moisture to be able to convect out. So right in here, you can see there's a little gap, and there's a little gap between here and here, which is noted right here. So any convection can go out here and also out here. So this is the detail you do. This is again over the top of the window. Same thing on the bottom of the window. It's disconnected from below. So you have to make sure that any moisture that gets in here goes up. This is how you deal with it on the bottom of the window. Same thing. Slopes and weather-resistant barriers, tapes, sealants. Again, everything is shingled over the next layer. Just show you that this should be sloped in here. All those leak, every single one. Brand new, brand old, doesn't matter. They all leak. Otherwise, they wouldn't have weep holes in them. Flexible facts. It's not a political statement. So the problem that we have here is that flex duct today used in residential applications was never designed for that. It was designed for a 5-foot section between a trunk line and a supply register in office and multifamily conditions, multi-floor office buildings. And it was done for sound. That's why it was invented, because the interior is very convoluted. It breaks up the sound by bouncing it around. It takes it from a very noisy trunk line. It also creates static pressure losses. I'm not going to go through this. This is at a 15% compression loss. And if you take a look, this is only a sag in it. So you can see this is a flex line right here, sag. You know, the difference in pressure in water column is between 2.75 and 0.5. So, you know, you've got 2 more inches of water column here, here than you do here, the other way around, sorry. But anyway, the point being is only with a 15% compression, and compression is the wrong word, I should change that. It's just a sag. That's all it is, it's just a sag. As compared to rigid 6-inch, there's like almost no difference at 400 CFM. At 160 CFM back on the flex, you're almost right about here. So that's a huge difference. These things have to be installed correctly. More examples at 30%, 45%. I mean, we're just getting higher. We even have to change the scale on the left-hand side. So you don't want that. And these are the reasons why. This is absolutely useless ducting, absolutely useless. This is not going to work in that. You probably just added 20 feet to this length, plus this, maybe another 10 feet or more. So this 4-foot section here is now equivalent to 30 feet long for pressure losses and flow rate drops. It's unbelievable. And this is done all the time. This is a $4 million house in California. Same house right here. It's unbelievable. And this is what you see. You know, you can't make this stuff up. You just can't. Same house. They have no clue about air barriers and air sealing. So the exterior sheeting was never even completed all the way to the corner. It stopped short of it on both sides. But they do have air sealing down here. Great. That's not really accomplishing anything. I don't know what they're going to do with this. They've got to take this whole thing apart in order to put another panel over the top, you know, dry OSB, and then put this back in again and cut the hole properly. Same thing here. I mean, here's an electrical box. So they sealed around the box. Look at the hole in here. And look at all these holes. It's absolutely useless. This guy is amazing. So instead of cutting a couple of holes with a hole saw or a drill bit, how are they going to fix this without? I'm sorry. How are they going to fix it without taking it apart? They've got to cut the pipe. They can't put another piece on the outside because it won't flush out. They've got to put blocking in it. I mean, just the redo alone is going to cost probably 5 times more than the original install itself. But they sealed the plate. Great. Doesn't work. How much insulation are we getting in this cavity? Not very much. These are design problems, guys. And it's a problem. It's a problem for inspectors. It's a problem for builders. It's a problem for all the trades. Other issues. This one I really love. Let's put the kitchen exhaust right over a vented window. I really like that. That's a really good idea. Again, baffles installed incorrectly. This one's almost all the way up tight here. This is useless. This one I can't even see. Don't forget, there's blocking across here to prevent, there's blocking across there to prevent any kind of ventilation. Why didn't they just cut this down 1.5 inches, talk to the, you know, or do it on the flat? If they did it on the flat, they'd be better, but they'd still be blocking their 1.5 inches. So bad detail, bad design. There's got to be a better way to do it. You can see it here. These are not stapled correctly. When these get wet, they will fall down. And not to mention that they've got holes in them, and they got a wire popping through. They got everything wrong here, as you see here. You can't use a hammer jacker to put these on. You need a heavier staple than that. You need more of them, and you've got to staple from here to here. Two up here and 2 down here don't work. They do make waxed cardboard, believe it or not. You can buy it. It's a couple of cents more per board. Or you can use the plastic molded stuff. Attic ventilation, I'm not going to get into. They're just calculations. Here's a great example of grade. I don't know what it is. It's way beyond grade 3. Again, you can't make this stuff up. Here's one that I like. This is an old house. This is in Seattle. Many, many years ago, they drilled and filled with a injection foam. In here, you can see some of the remnants of it. They peeled everything off all the way out. If you look closely on these little button vents, you can see that they're all sealed off from some of the foam that's still on there. So they were trying to figure out on this 2x4 wall, again, there were parameters. They had no budget to take the siding off and redo it. And on the inside, it was all plaster as well. So they took the plaster off, but they left all the interior trim on. So what we had to do in order to get as close as we could, you know, to an R20 wall, again, this is a remodel, without furring out the walls, taking off all the window trim and all of that. What I did was I designed something. So this is not the sheathing. This is actually the clapboards right here. So there's no sheathing on this wall. So there's no air barrier, not to mention the vents, but everywhere between the shiplap you get air infiltration in here and water. You can see some of the water stains on this side right here. You can see another one right over there. So the water gets in, but this had so much drying potential that it didn't matter how wet it got, because there was no rot in this house whatsoever. It's over 200 years old. So what I did was I gave them an air gap right here. We really only need 3/16 of an inch, but I gave them a ½ an inch. And then I used polyiso, again, foil face out, because that's the water resistant face. You fit the two pieces together first into the wall cavity, take them apart, again, tape to the outside, because we want the pressure from the outside pushing against the tape. And then you can fill the rest of it with any kind of fibrous insulation. This shim space here allowed me to do the ½ inch in here, because it's the same, it's still a 2x4 wall. We just projected it out a little bit and matched it up so you could put drywall on it and not have the same, the 3/4 of an inch thickness of plaster. And what will we get? We get an R16 cavity out of the deal. Not too bad. So that's the way you can do that. This is a problem. Inspectors, and even inspectors and contractors and builders on here, please pay attention to this. You can't use the same width bat in manufactured lumber as you can dimensional lumber. You must use, in a 16-inch on center, you have to use a full 16-inch bat. You can't use 15, okay? It's only 14.5 on dimensional lumber, but it's actually 15 5/8 on manufactured. So you have to go to a full 16-inch bat if you're going to use bats, and you have to go to a full 24-inch bat if you're up in rafters or other systems that are 24 inches apart, because the distance here is greater than the distance here, even though they're laid out on the same schedule. And what happens is you create these 5/16 gaps on either side of every single cavity. So, you're almost you're 3/4 of an inch basically on each side, on each cavity of a gap, all the way from the top and the bottom. Holy smokes, that's crazy. Anyway, you have to order the right material for the right length, and part of the problem is that the manufacturers don't tell you this, because all of the manufacturers put these numbers and this data in metal framing. So if you're not looking at metal framing, you would never know that these bats have to fit in here in order for them to work. So manufacturers are pretty guilty. If you're filling insulation with a blown-in system, you have to test it for density. You can't just put your hand on it and feel it and just visually walk by it and say, it's got the right density so that I know that it is the correct R value. Now you can see that this stuff will stay in place. This is hard to pull out. You can actually take the facing material off of it that's only used for installation if you want to, and it will all stay in place. Nobody does it because it's a waste. There's no reason to do that. And sometimes it's a vapor retarder. A lot of different systems you can use. But basically, you're going to have to remove a cubic foot of material. And then after you move it, as for a standard width cavity, you're going to have to measure the length based on the width and the depth. You're trying to figure out what that cubic volume is, because you need 1 cubic foot, because that's the way it's described by the manufacturers. You weigh the sample. So you weigh the plastic bag first, you carefully put the material in the plastic bag, and then when you're done with that, you weigh it again, subtract the weight of the bag from here, and it tells you what your sample is with your target. For our material, it's 1.8 pounds per cubic foot. Cellulose is 4.3 pounds per cubic foot material for cellulose. To get not even the same R value, you get a lower R value actually. And it's got to be laid out, and it's got to be marked. Okay, this is a double wall, so you can see how deep it is, but this area right here is very shallow, okay? And that's because it's 24 across, and, 24 across and 12 inches deep. So you do your calculation. This is not 1 pound 9 ounces. That's 1.9 tenths of a pound is what that is. I wrote this wrong. Here's the date I did it. Here's the measurements I took. Everybody can repeat it. They know who did it. They know when it was done. And they know the actual weight of the sample, and it falls within spec. That's all you care about. Okay, so if you don't do this, you don't have a warranty from a manufacturer because they can't guarantee what the R value is because you determine that by what the density is. And the other thing is, this is in every code that I could find in 2003. I labeled it right here for you. The installed density has to be listed on the certification. So if it's not listed, they didn't do it. If you don't see it when you're inspecting, they didn't do it. Okay, they can tell you they did it, but there's no proof. Okay, and you need to do one of these on the first 4 or 5 cavities, and that's because you don't want to get all the way to the end and find out you're too light or too strong. Too strong, you wasted material for no good reason, and if you're too light, you're screwed. You got to go back and check every cavity. So you do it on the 4th or 5th cavity, and then about every 500 square feet. That's all you got to do. It's easy. Weigh the sample. Owens Corning has a gadget that they use that forces air through it, but it's a piece of equipment that you have to buy and lug around. You also have to have a compressor and air hoses and electricity and all that stuff. So easiest way is to weigh the sample. And again, give you an idea of what happens. So like on a 2x6 wall, it's 5.5 inches deep on 16 inches on center. Your vertical cut's going to be 21.5. On a 24-inch wall, it's only going to be 14 inches because you have greater width. And then if you go like to a 2x10, it's going to be 13 inches, or if it's 24 inches on center, it's going to be 8.5 inches. So these vary all the time. So you've got to do the calculations if you don't have a chart to get you where you're going. Okay, so I'm done with my spiel. And anybody who's got any questions, I'm here to help answer those.
Great, thanks. And just, I'll let the participants know, I'll go ahead and submit this. Since we are 30 minutes over, I'll submit this for 90 minutes for ICC CEUs instead of our normal 60. So appreciate y'all staying the extra half hour. I still have 111 people on, so evidently you're talking something that people are wanting to hear. Got a couple of questions on the webinar, and then I've got a few that were sent in. Let's see. Can you talk? We're seeing more homes with stucco rather than brick. The issues are even magnified and exposed a lot quicker. Can you talk about applications when using stucco versus brick and the differences?
Sure. So let's just start with the brick because, the simple solution in brick is to create a drain plane behind the brick. Bricks are sponges. They're very hydrophilic. They soak up and hold on to a lot of moisture. So when that moisture gets released, it gets released in 2 directions, again, depending on the conditions. So that gap behind there, which was originally measured by the mason's thickness of his fingers, when he put his brick down, he would leave, his fingers would determine what that gap was. Today we talk about a 2-inch gap between the back of a mortar, brick, block, rubble, whatever, behind that for your drain plane. And then the wall system behind that gets treated just as any other framed wall system would, or even if it's a block wall system, you still have to have weather-resistant barriers, drain planes, etc. For stucco, it's a little bit different. So let's take a 3-coat stucco. I know in the Southwest, they do a lot of 1- and 2-coat stuff for stucco, but basically the system should be identical. It doesn't matter whether you're going to use an EIFS system, where you're going to have pink or blue board or rigid board up first. Behind that rigid board, again, you need the drained capillary break, 1/16 of an inch or smaller. You can get that by your WRB. If you don't have a WRB, you can use 2 layers of felt, not 1. And so the WRB automatically creates that 1/16 of an inch gap. But what happens for stucco is either you have that stucco wrap or drain wrap before you put your wire up, before you put your brown coat, scratch coat, what have you up, before you do any of that stuff, those 2 layers go on top of each other. Then your wire gets installed. And those 2 layers, what happens is when your first cement-based coat goes on, it actually adheres to the outermost layer and then actually pulls it away. So there's a small capillary break between the 2 layers. So that works for stucco. And then you would just proceed as as normal, you would, you know, put all your stops in around your fenestrations, and you would install your stucco the same way. Every penetration has to be sealed, you know, so you know, your stucco is going to go up against your grounds before you put your exterior trim on, and making sure that you have a sealant between the stucco and the rough ground before you put your trim on at there, so that water can't be introduced into that. Again, everything has already got 2 layers of paper on it, or a drain wrap or a stucco wrap. Does that answer your question?
Yeah, and then another one is basically talking about encapsulating attics and how, you know, how nice an attic is when it's fully foam encapsulated in the summer in Texas. And he's talking about if bats have a better R value, maybe just your thoughts on an encapsulated attic with a fibrous material rather than foam. And you know, you covered it pretty well as far as, you know, having that rigid foam in the condensation control. But in regard to like a hot, humid climate like Texas, what do you think about a fibrous material encapsulated attic rather than a foam?
Okay, so when you say encapsulated attic, you're talking about a conditioned or a semi-conditioned attic that's
Yes,
unvented?
yes.
Okay, so the same rules apply for the same climate zones, for the same condensation control on top of the attic if you use a fibrous insulation. And are we talking about a full open attic where the ceiling is the insulating plane, or are we talking about a cathedral or a vault?
No, it sounds like a cathedral. I mean, he didn't specify in his question, but I'm guessing more of like a cathedralized type of attic, or even just where you want to insulate up against the roof deck with the fibrous material and bring your mechanicals into conditioned space.
Right, easy to do. Again, fine in the hot, humid climates, no problem with it. Condensation control up top, fill the caddy with your favorite fibrous material that you like, and put your air barrier in there, remembering that that assembly, let's see if I can find that real quick. Looking for that roof assembly.
Yeah, and I'd like to point out to the inspectors still on the webinar, when you get there, that chart showing the R5 continuous requirement in climate zone 3 out of 806 for condensation control. You don't see that. Most
Yeah.
inspectors don't pay attention to that.
Yeah, I mean, so again, just repeat the same 2 options. Obviously, you can do this with a fibrous material. You have to make sure that these are airtight assemblies. That's the key. You don't want any interior warm conditioned air getting into this assembly. Okay, this would be this would be your air barrier against your roof deck. Here, it would also be added to your insulation. So if you, excuse me, if you needed a 49 here, let's say you put an R10 here, you only need a 38, basically, down in here. The drywall on the bottom has to be airtight. That means you have to seal all the edges of the drywall, and you have to seal the top plates, all top plates, interior and exterior, because you don't want that connection into either an open attic assembly or where it might connect, a wall might run all the way up to the underside of the bottom of the rafter if it's a cathedral or a vault. As long as this is airtight, again, you got to deal with the details on the edges, very important, and you have to have a membrane across this sheathing here. I don't think it's identified. It's not identified here. But you got to have a membrane in here. Again, it has to be turned down on all sides and edges so that you cover this seam in here so not allow any air to get in or escape. Whatever this is, it's going to be somewhat permeable, whether it's, you know, a cover board or whatever kind of sheathing you're going to use. And then on top of that, you put a peel and stick layer on top of that, and that wants to be permeable if you're using this exterior insulation. If it's here, it wants to be impermeable. Water control layer right there. So that's really the way you do it. And you do it this way in all climate zones. The only difference is how much insulation you need in the cavity and how much you need condensation.
Okay, and then just a couple more. Craft paper for climate zones 2 and 3. I typically, 25 years ago when I was training under an inspector, it's like, oh, you put the paper on the warm and the winter side. And then I get questions out of Houston. Every once in a while, somebody will call me, hey, I got a job. They're using craft paper. They can't use craft paper down here. Can you just a comment or two about the craft facing on paper in hot, humid climates?
Yeah, in hot, humid climates, it's always best to have your vapor retarder facing out. In other words, you're warmer and more humid most of the year as opposed to not, okay? You also have cold air on the inside. You're using air conditioning. So remember, everything goes from more to less. So hot goes to cold, wet goes to dry. So if you have warm, moist air, doesn't even have to have a wind. The pressure difference, just because of the difference in temperature, is going to be higher on the exterior side of the wall than it is on the interior side. So vapor retarders want to face the outboard side in hot, humid climates. You can do that a number of different ways. You can use a craft bat. You can not use a craft bat. You can use layers of roll goods on the outside, permeable air barriers. Tyvek is a permeable air barrier. There are a lot of different smart vapor retarders that are very expensive you can use as well. Basically, humid climates, the craft wants to face out, and in cold climates, the craft wants to face in towards the warm side in winter, like you said.
We don't see it much at all. Typically, the only place that I'll regularly see it is in that garage wall separating the house, just because there's not sheathing on the other side to hold it in, so they'll just use that. Oh, I did want to mention, I'm not a big fan of inset stapling for craft facing either, and learned at the ResNet conference, where I conned Rick into doing this webinar for us, that the new ResNet protocol for you are going to, by default, have to give that at best a grading of a grade 2 installation for craft face inset stapled bats with the new ResNet protocol. And then the last comment I'd like for you to just a little bit about the way they manufacture Tyvek and its permeance versus that woven perforated cheap builder grade weather resistant barrier. Do you have any thoughts on those two products?
I'm sorry, the difference between which two, a weather resistant barrier and what?
Well, like the way they manufacture Tyvek versus the way they manufacture the woven perforated builder grade knockoff Tyvek.
Yeah, so there's a major difference between the two. And the best way I can tell you to learn why you have to test these things before you use them is a building science white paper, and I think it's called Leaks and Holes, L-E-A-K, as in building leak. I'm going to get out of here and see if I can find this for you really quick.
I've seen the construction instruction guys presentation on it, and it's pretty eye-opening, and I think they got some of their graphics and information from this white paper you're going to show. It's pretty eye-opening. I wish I would have known when I was a building official to give my builders better advice about that, because I had a couple of builders switch to that, and frankly, I just didn't know enough about it at the time. And I really, my builders trusted me, and I could have talked them away from it and directed them to continue using the Tyvek or a similarly manufactured product. But frankly, I just didn't know enough at the time and didn't have the time to go through the
the thing. I'm sorry, I interrupted you. Sorry.
Oh, go ahead. I was done.
Let's see if I can find this real quick here. Holes and leaks. This is it. And what Joe does is he goes through this whole test procedure. It's very simple to do. That way you can take a section of your material, like right here, and you can actually test it and see whether or not here he's boiling some cedar and other wood in here, so because he wants that liquid, just like it would form over time on the back of your siding that's unpainted, and you just want to see what goes through it. So leaks and holes, or is it holes and leaks? Building Science Corporation, BSI-066, holes and leaks. If you go through that, it'll tell you exactly why. I've seen Mark LaLiberte on a site. He and I were at a site together, and he took a bottle of water and turned it upside down on one of these builder wraps and just let it dripped right through. He didn't even have to squeeze it. So that's a quick test on site. But yeah, there's a big difference between the materials, and within the material itself, especially things, the fancy ones, you know, Tyvek, Hydrogap, and all these others, they all have different permeability rates, and many of them are variable permeability rates, so they change with moisture and energy. So you got to make sure you know what you're doing. Remember, we want everything more vapor open to the outside than it is to the inside. So,
Right.
yeah.
Okay, and then my first ever question about climate zone 6A and 6B, and this is the last one. For exterior wall residential application in climate zone between 6A and 7B, do I need vapor barrier control? If it does, what side of the wall does it need to be on?
Well, if you're in a cold climate zone, it wants to be on the warm side of the wall in the wintertime, which is most of the time in 6 and 7, more than it is hot. So the vapor retarder wants to be on the warm side of the wall. Again, plastic is a vapor barrier, and other than plastic, you have a variety of choices for vapor retarders. So you want a vapor retarder that's considered, defined as a permeable air barrier. Again, we go back to the Canadian solution where they like plastic because they just don't understand that you can have an air barrier that's permeable. And Tyvek is a great example. It's not designed as an interior vapor retarder, but there are many products, including Craft Face, if it is face stapled. All right, face stapling, no side stapling because it won't pass. Too many air gaps through it. So face staple your vapor retarder if you're going to use a Craft Face bat. Make sure it's tight to the top and the bottom. Make sure it's fully filled. Make sure it gets around all the obstructions that are in there, wires, pipes, whatever those obstructions are. Just make sure the bats are split around it, and that you can solve what you need to do as far as retarding air. That's the thing we want to do, or stopping air and retarding moisture flow. That's really what we're trying to do more than anything else. Anybody? I'm sorry, go ahead.
Do you mind sending me we typically like to send a PDF of the slide deck out to the participants. Do you mind emailing me a PDF of your slide deck?
Yeah, no problem.
Okay, great. And I guess that's it. Thanks everybody for joining us. Wow, great information. Rick, I'm ready for another one in a month or two. Let me know what else you want to do for us. I really appreciate your building science knowledge, and great presentation today. I can't thank you enough. And thanks everybody for joining us this morning. Stay safe out there, and we'll talk to you again soon. Thanks again, Rick.
Yeah, just one more quick thing. Anybody that needs to, anybody that wants to, if they want to, reach out, please go ahead and do that. My email is on the slide. You can actually get it from Jason as well, and my phone number is there too. This is what I do 24/7, unfortunately, but you can pretty much contact me anytime. Any questions you need, any problems you might have between, different opinions between a builder, contractor, building official, inspector, whatever, architect, and these designers and engineers, give me a shout. We'll see if we can help you solve.
That's certainly. I've always not only appreciated your building science knowledge, but frankly, I like somebody that's not afraid to tell it the way it is. And I appreciate your candor as well, for sure. So be prepared.
All right. Appreciate it. Thank you so much. And Jason, I'll be in touch and we'll figure out another one.
Okay, sounds great. Thanks a lot.
All right.
Everyone have a great day. Bye, everybody.